All right, grade 8s. We're moving on to the last section in chapter 6 here, graphing linear relations. We're going to look at actually plotting these things on a graph. Okay, so we'll get right into this first example here. You can look at it in your book as well. Just for some context, I'm not going to read through the whole thing, but we've got these banners here. The motto is 50 centimeters wide. These are both 20. Right, this is 20. This is 20. And this is 50. So basically, depending on where you want to put them on the wall, you might have a few of the mottos in between. So you're basically adding a 50. And so they say that the length of your banner is going to be 50 times n for however many, and then 40. So you can see where the 40 comes from, the two 20s that are always going to be tacked on the end. Okay, so explain each term in the equation. What does each term represent? Well, that's where the 40 comes from, the 50n just comes from. You might be putting an extra 50 centimeters for each motto that you're putting in between. Okay, use the equation to make a table of values. So we did some of this in 6.6. So if I take this, I have number of mottos, and then I have the length of the banner. N and L they use, and so I can take 1, 2, 3, 4, 5. So we usually do 4 or 5 to start, and then we can plug in the length, right? So if there's just 1, you're going to get 1 times 50 plus 40 is 90, right? If there's going to be 2, I plug in 2, I get 100, 140. Okay, and basically you know that for every banner that you add, or any model that you add, you're going to add another 50, so you might already be able to see what pattern is going to emerge here when you plug in the table of values. Okay, so then the stuff that's going to be new in 6.7 is that we're going to actually graph the relation. So most of them I'll give you graph paper to do, like on a quiz or something, but sometimes you may have to actually just construct your graph. Now, graphing is a little bit tricky. Students sometimes want to take the easy way out. They just want to say, okay, 1, 2, 3, 4, 5 along this side. So the first column is always going to be your x, your independent variable. And then, oh, the numbers are 90, 140, 90. So I'm just going to do 90, 140, 190, 240. But it's actually not accurate, because on your graph you have to, if you're making this a certain distance, it should be the same distance every single time. So I can't really just jump 90, because then if I'm saying this is 90, this should be jumping 90 as well. So you kind of want to just estimate and pick something that's going to work. I think for this situation, 50 might work nice. Now you're going to have to estimate a little bit. 200, 250, and then 300. And depending what our numbers are, we might have to play around with what scale is going to make sense. You don't want to use your whole paper up just to make one graph, right? So here, my first point, we talked about the coordinate points, or the ordered pairs, 1 and 90. So for 190, so we're just going to try to do our best. If you have grid paper, you're going to make this look a lot nicer, right? 2 and 140, somewhere there. 3 and 190. 4 and 240, somewhere here. Be a little high, but, and then 290 here. But the general gist of it is that we're kind of jumping up. Notice it makes kind of a straight line. Okay, what can you find out from the table of values and from the graph? Well, from both we can tell that this is a linear relationship. It's going up by 50 every time. And you can find the specific lengths for each number of banners. What you'll notice is it doesn't really make sense to take 4.5 banners. You're not going to cut half a banner, presumably, right? And so we'll get more into that in the next, or a little bit later on when we talk about discrete. Okay, so we'll look at a different example of that too. This is under the Connect. You guys can read through that on your own, I think, for the most part. But they give us number of plants for tomatoes, or no, sorry, $6 for every tray of tomatoes you plant. So trays, okay, for the total. So you can see that this is a pretty straightforward, it's a one-step equation, so it's just $6 per one. So making a table of values, 0 and 0, so if you don't work, you get nothing. If you do 1, you get $6, 2 and 12, 3 and 18. You can see that they plug that in on the graph here, 1 and 6, and you can see that for every 1 across, you're going 6 up every time. Okay, this is where we'll talk about discrete, right? So the points line is a straight line on the previous graph. Since Sylvia only gets paid for whole numbers of trays planted, we do not join the points. For example, Sylvia is not paid for 1.5 trays planted. These data are called discrete. Okay, so when you can't join the points together, when it doesn't make sense to join the points together, we say they're discrete, right? So another example that I often use is like selling hats or something like that, or bananas or whatever. You can only sell one hat or two hats or three. You can't sell 3.74 of a hat. So on a graph, it doesn't really make sense to join the points. You can sell one hat or two or three. So we call that discrete. Otherwise, we would call it continuous. Okay, and continuous, it does make sense in certain situations if you're talking about, for example, speed over time or distance over time, and you're traveling a certain place or something like that. Well, you could travel for exactly 1.37 minutes or something, right? You can travel exactly 49.7 kilometers. It makes sense to join the points in a straight line. So that's continuous. Some of the examples you'll be asked to determine, does it make sense? Are they discrete or are they continuous? Okay.